Alright, welcome everyone to the second video here on colligative properties. We're going to talk about osmotic pressure. So what is osmotic pressure? Osmotic pressure is related with this process of osmosis, where if you have two liquids separated by some membrane that allows the solvent to pass through, but not necessarily solutes, okay, that the solvent will flow from low concentration to high concentration right sides of this membrane, right, because of the difference in the chemical potential between the two solutions, right? Again, everything eventually wants to reach an equilibrium, right? And that equilibrium is established in terms of phases and reactions and other things like that related with chemical potentials being equal across the entire system, okay? And so, right, and so every solution will have this transfer of solvent from a lower concentration to higher concentration system, right? Think of it as sort of transferring of temperature from high temperature to low temperature, though again here you're going from low concentration to high, okay? Type of a thing, right? Until you get equal concentrations across this membrane. Now, the osmotic pressure, which is often given by the symbol capital pi, is the pressure required to keep the solvent from doing exactly that, right? From flowing from a low concentration to high concentration solution, okay? So, how do we calculate what this pressure is? Well, as we've been doing for all these other colligative properties and things like that, it all comes down to looking at the chemical potentials, okay? So what we're going to look at is comparing, right, we have, right, the solvents separated by a semi-pure membrane, right? On the left side, I have some low concentration, let's assume pure solution, right? On the right side, I have some solution, has some mole fraction of A, right? And I'm applying also a pressure on that side, okay? Right, because again, if I don't apply any pressure, right, between my pure liquid and my concentration, right, system, then there will be a flow of liquid from the pure side over to the concentrated side, right? But if I apply a pressure on the concentrated side in order to keep any liquid from flowing in, right, then I can maintain this equilibrium between the two sides of the semi-impermeable membrane, right? And so now we just got to figure out, okay, well, what is that pressure I got to apply? Okay, so we know that because of the addition of a solute, right, the chemical potential of that liquid on the right side is related with the pure chemical potential of that liquid plus then RT ln of the mole fraction of that liquid, right? Assuming an ideal solution, right, an ideal dilute solution, okay? So Raoult's law, right, so we have that, right? And then we've shown before that some change in Gibbs free energy under constant temperature, right, due to a change in pressure, right, of a liquid, right, is just an integral of that change in pressure, right, and so, right, and then the change in chemical potential, right, is just the molar Gibbs free energy change, which will be related with the molar volume, okay, and so the chemical potential of a liquid, right, with the addition of some external pressure, right, is just equal to the pure chemical potential plus pi, or plus the molar volume times that change in pressure. Now here I'm assuming I go from some initial vapor pressure P to some vapor pressure plus this extra pressure, which I'm calling capital pi, okay, this osmotic pressure that we're applying. So if I combine then, right, that first equation, which is saying, okay, the chemical potential of my pure compound on the left side of my membrane, right, so the left side of this equation here, right, this is your pure solvent, right, that's on the, right, if you had some membrane, right, that's, you know, on the left side is the pure solvent, on the right side is the mixture plus the osmotic pressure, right? And so I have, again, what the impact is of adding some solute to the chemical potential of my solvent. And now we have the impact of applying a pressure on the chemical potential of the solvent. So combining those two things, right, I get that the chemical potential, right, of the pure solvent, right, is equal to chemical potential of the pure solvent at the same pressures, right, plus this molar volume of the solvent times this external applied osmotic pressure, plus RT times the natural log of the mole fraction of A. Right, simplifying this equation, you get just negative molar volume times osmotic pressure equals RT mole fraction of A. Okay, we're going to assume that we have a dilute solution, right? So the mole fraction of the solute B is much less than 1, which is what we did for right boiling point and freezing point changes. Okay, so this natural log of A is just related with the natural log of 1 minus B, or chi B, which is just negative chi B, yeah, which is approximately the number of moles of B divided by number of moles of A, right? Because again, we're assuming that chi B is much less than 1, right? So I have a very small mole fraction of my solute, which means the number of moles of A is much greater than the number of moles of B. So the total number of moles is roughly equal to the number of moles of A, okay? And so then plugging that in, right, get this this molar volume of your solvent, okay, times the osmotic pressure equals RT times the number of moles of B divided by the number of moles of A, okay. Dividing over the molar volume of the solvent and using the fact that the molar volume of the solvent times the number of moles of the solvent is just equal to the volume of the solvent, right? You get that the osmotic pressure just equals the concentration of B times RT, right? So this equation that may or may not be familiar to you, right, is what we get out of here, right? Very simple equation, right, that the amount of pressure that needs to be applied is related with the concentration of B times temperature times our ideal gas constant.